All right, welcome everyone, and thank you for joining us today for this live demo webinar. I'm Ahmed Ibrahim, software engineer at Solid Sands, and today we will be getting familiar with the SuperTest compiler test and validation suite. As a software engineer here, I am involved in the development of SuperTest on a daily basis. So it brings me great pleasure to be able to introduce to you in this webinar who we are as a company, a quick overview of the main products we offer, what exactly is SuperTest. After that, I'll showcase how SuperTest can be employed for compiler qualification. And then finally, I'll perform a live demonstration of its functionality. Then I'll wrap up and take in any questions at the very end. So these are the topics of today's webinar, and I'll start with an introduction to who we are as Solid Sands. We are an Amsterdam-based software company specializing in compiler and library testing and qualification. And every day we improve the quality of C and C++ compilers, libraries, and analysis tools while enabling their safe and secure use. We provide services for companies in the semiconductor, compiler, and security industries, as well as companies that develop safety-critical software in the automotive, robotic, and railway industries all over the world, spanning 3 continents, as can be seen here on the map. Now that I've given some background about us as a company, we can move on to the products we offer. And for that, we have 2 primary products, SuperTest and SuperGuard. And SuperTest is our test and validation suite for C and C++. So it tests compiler and standard library conformance to the ISO C and C++ specifications. As for SuperGuard, it is designed to support the qualification of the C and C++ standard library implementations for safety-critical applications. But for the purpose of this webinar, we will be focusing on SuperTest. And to begin with, you might be wondering where it would be ideal to adopt SuperTest, and 2 primary scenarios come to mind. The first is if you're developing a compiler and/or standard library implementation, and you want to enlist the help of a massive test suite with a great variety of test cases in order to check their quality. Another ideal scenario would be if you're trying to qualify a compiler in order not to produce faulty code in line with functional safety standards. So SuperTest is a very suitable choice if you are pursuing compiler development or qualification or both. So let's provide an overview about it. So as an overview, SuperTest is used to test compiler and standard library conformance to the ISO C and C++ specifications. And to do that, it contains a comprehensive test suite of both handwritten and generated test files. It has tests for the front end and back end of the compiler, but also for analysis and optimization passes and code generation. For example, the C and C++ standards do not provide specific guidelines or requirements regarding optimization flags. However, by virtue of our compiler experience, we are aware of how different optimization levels and flags significantly impact the code generated by the compiler. And this is precisely why we developed a comprehensive optimization suite where we can effectively verify the correctness of optimizations that are applied by a compiler. So now that we have provided an overview, we can delve into further details, and here are some of them. So SuperTest has tests for all versions of C and C++, ranging from C90 to C18 and from C++03 to C++20. And in addition to the thousands of handwritten tests, there are also multiple test generators. For example, the depth suites contain generated arithmetic tests that can be configured to match the data model in use. To illustrate, tests for 16-bit integer arithmetic would be quite different than tests for 64-bit arithmetic, as you would imagine. So here we can guarantee a suitable depth suite for an exact data model. Other examples of test generators are our calling convention tester, which verifies correct handling of function arguments and return values, as well as our template-based test generator called Tempest. And it's also possible to easily create your own subset of tests if desired. For example, if you have a target that doesn't support floating point, then it's easy to exclude all floating point related tests from a particular test run. And finally, we've developed the test driver in a way that makes it very easy to script, so it can actually be configured for any C or C++ compiler, as well as any execution environment. There are also numerous example configurations that are readily available to help you get started. And after running the tests, comprehensive reporting will be available in a friendly human readable format, such as plain text. But it can also be available in an accessible web-based format such as HTML, or even in a structured and easily processed format such as XML that can be used in a continuous integration environment, or finally in a lightweight spreadsheet format like CSV. These were some of the relevant details of SuperTest, and we can now take a look at the test driver's interactions. So for illustration purposes, here is a simple overview of SuperTest's test driver in action. In essence, the test driver interacts with the compiler in use by compiling and linking tests on it, after which it expects to receive compile time results and diagnostics along with an executable in return. Following that, the test driver interacts with the target device in order to run the generated executable retrieved from the compiler, and it receives the runtime results and diagnostics in return. So we have two interactions in total here, and from the first interaction, the test driver receives a compile time result. If it's a failure, then it shows up as a compile time failure and signals that compilation was unsuccessful. However, if it was successful, then it shows up as a compile time pass and produces an executable, which the test driver retrieves and provides to the target in the second interaction. And it does that in order to retrieve the runtime result from the target device, and from there it either reports a runtime pass as well or a runtime failure. So these are the interactions taking place in a nutshell. So now we can take a closer look at the test suite. And to demonstrate the magnitude of the test suite, it can be showcased here with numbers. So on the left-hand side, we can see various relevant subsuites with the lines of code contained within each one, as well as the language standard they are applicable to on the right-hand side. Now, if we zoom in on the summary figures, we can see that the sum of the core suites amounts to approximately 1.7 million lines of handwritten code, whereas if we generate a single depth suite for a particular target arithmetic, it would end up generating about 11.5 million lines of code, which demonstrates how effective the depth suite arithmetic tests are. So now that we have some measure of the test suite's scale, we can look at qualification. So by now we've seen how testing is a viable method for quality assurance. However, it is just as useful for compiler qualification. And for many standards spanning functional safety in the automotive, railway, and medical industries, it becomes crucial to present evidence that a software tool complies with its specification. And since any C or C++ compiler's specifications can only be derived from the ISO C and C++ standards, then this compliance and conformance can only be feasibly performed by virtue of a validation process. And thus, the SuperTest validation suite has proven itself countless times for that exact purpose. And we know qualification is crucial since no matter how good the software employed is, if the compiler is not qualified, then it becomes an immediate safety concern. So now a critical component in proving compiler qualification actually comes in the form of a traceability report, of which we have an example laid out right here. Now, this is a report containing traceability between each and every section in the C and C++ specifications, as well as the corresponding test results. So for T7.c that lies here within the suite in folder C99, subfolder 678, it can be directly traced to the C99 standard, subsection 6.7.8. And each section from the standard is marked with passed, failed, or gap, and with corresponding explanations. So in this sample report, we have one test that encountered a runtime failure, as well as one gap here that indicates a failure of retrieving a particular test's results. In case of failures, they can be thoroughly investigated within the validation suite in order to determine their cause of failure. So it's not the objective to assume a completely error-free run for any compiler. It's actually much more important that any failing tests end up being documented and their detrimental effects or negative effects mitigated. So a good example would be for particular constructs of the language that do cause a certain compiler setup to fail. The developers, let's say, of an application could be made aware of such constructs to document their effects and avoid them in source code. And such an avoidance would then ensure that the erroneous constructs are not encountered by the compiler. Now, this traceability report forms the evidence that tool qualification was performed as required, which brings us to an important element for the qualification process, and that is how the compiler is used, which is our next topic, which is the use case of a compiler. And the use case of a compiler is the way it's being used. It's defined by the version of the compiler, the target processor intended by the compilation process, the version of the C or C++ language, the combination of all the compiler options in use, and potentially also the options of other tools being used in the compilation process, such as a linker or assembler. If any of these variables are changed, then the use case is consequently changed. For example, if the compiler is upgraded, then the version is changed. Now it might perform differently than the older version. If the compilation intends a different target processor, then it might generate completely different code. If a different version of C or C++ is intended, then the specification for it immediately differs. And one of the most obvious is if the compiler options change, such as with adding optimization levels, for example, then the compiler generates completely different code. So when a compiler is being qualified for functional safety, it should only be qualified for the exact way or use case it is being used. Only that way can we guarantee that the use case's compiler flaws are taken into account, paving the way for it to be used in a safe manner. Whenever any of the aforementioned factors change here on the screen, then requalification becomes immediately necessary. So now that we've covered the importance of the compiler's use case, section traceability reporting, as well as the test suite in numbers and the test driver's various interactions, I believe we can start with the live demo. So I've went ahead and already downloaded the SuperTest demo, which can be requested from our website. And we will be discussing 4 configuration files that are of particular interest to us. And those are the top-level configuration file, default.cfg, as well as 3 configuration files within the target directory, and those are the cval target header file, the stplugins script, as well as the user.c file. And I have opened them up in my code editor here for ease of access. So we can begin with the top level configuration file. And in here we have three important variables, CC, C flags, and lib flags. Now, CC is the compiler's executable. And by default, for this demonstration, we're going to be using GCC. C flags here represents the compiler's flags and options. And for this demonstration, we're enabling support for specific features and behavior in the C99 standard. Whereas lib flags represents any libraries that are to be linked, and we're linking the mathematical library by default in here. And take note that the combination of these three variables forms the compiler use case that we just mentioned. Another important variable in the top-level configuration file is the test set expression. And for the purposes of this demo, we have it set to a predefined list of about 100 tests, slightly less than 100 tests. But to demonstrate in the actual product with the larger suite, it can be set to, for example, CXX17 to target tests that are specific to the C++17 standard. And then, for example, you can make use of arithmetic in order to deduct any tests that belong to sets that are not desired. For example, here you can deduct tests with floating point arithmetic. And then we can move on to the cval target header file. And this is a header file that configures macro definitions for a specific compiler use case and target. This is done by including the header in every test file in the suite, so the test files can use these macros to select the appropriate test cases. So these macros that we have right here configure if the compiler or target supports specific features that are not always supported, such as complex math and floating point arithmetic. And then two further macros that are of importance to us are the cval exit and the cval put char. Now, these macros configure how test executables report their result and diagnostics to the test driver. By default, we're using exit and put char as functions, and these will typically only work on a target running an operating system. In the case of a target without an operating system, however, such as freestanding implementations, then these macros can be redefined to call a function that has a breakpoint. That way, even the smallest, simplest debugger can still read the test result from a variable. And these functions can be custom defined in the user.c file. And this would be an ideal place for it. Now, this is a file that is linked with every test, which makes it an ideal candidate to custom define these functions. This file is empty by default. However, for this demonstration, we're showcasing how it can define the functions for a target debugger. So in this simple example right here, it defines a custom exit function that stores the test result in a global variable and then calls a function that triggers a breakpoint. That way, the debugger can then read that global variable in order to obtain the test result. And now we move on to the fourth and final configuration file, and that is the ST plugin script. Now, this script acts as an interface between the test driver and the compiler, as well as between the test driver and the target. It has two important plugins to discuss. We've already skipped forward to the first one, which is the compile and link plugin. Now, this plugin constructs a string with the parameters taken directly from the top-level configuration file right here. And it creates a string with them, which is then supplied to this run function right here that would invoke compilation just as you would on any command line interface. So you start with the compiler's executable, you type the compiler flags, you add any include directory of any header files, you add the test file paths, and the library flags, and so on. Afterwards, the compilation result and generated executable are returned to the test driver. So by virtue of this plugin, we have completed the compilation process, and now we want to run the generated executables. And to do that, we have the second important plugin called run test right here. And in here, we want to run the generated executables. And this is done by constructing a command that starts with the test executable and then adds possible arguments to it. And that executable is again executed in a very similar fashion as you would on any command line. And the result is again returned to the test driver. So the test driver can analyze whether execution has passed or failed at runtime. Now recall that the demo configuration here uses a host compiler. So the test executables can be directly executed on the host. However, if you're using an embedded target, then this run test plugin can be easily scripted to flash and run the test executable on the target, for example, with a debugger, like in this commented section right here, where the script sets a breakpoint, and then it runs the test, and then it exits with the test result. So rather than running the test executable directly on the command line, it is now provided as an argument to the debugger, and that debugger is then invoked by the run test plugin. So now we can invoke the test driver. And to do that, we invoke the strun command. Now, the test driver has both a command line interface and a graphical user interface. But for convenience, we'll be using the command line interface. So to do that, we type in strun. We have to supply a configuration. So we will be using the top-level configuration file that we have seen earlier. And then we add a P flag right here, which stands for progress, and that allows us to see the progress of the tests that are running. And as we can see, it starts by removing any existent log directory in order to ignore previous test driver runs. And then it loads the ST plugin script, which we just saw. It was the final configuration file we discussed. And then it runs a configuration test. And this is a small internal test to verify that the compiler can successfully compile and run valid tests while correctly detecting failing tests. So now we can investigate the outcome of the test driver's run by invoking the streport command. And in here, we need to supply it with a log file. So we will attach streport log. And that way, we can check the latest test run's results. And as we can see, here we have it in a neat tabular format. We can see we have one runtime failure or error and one compile time error for a total of 2 passed tests and 94 failed tests out of the 96. And then we have a particular designation here. We have tests that start with different letters. And this is actually an important designation in our suite. So tests that start with the letter T are t-tests, and these are valid tests. So any compliant compiler is expected to produce an executable for them. Whereas tests that start with the letter X are X-tests, and these contain erroneous ill-formed constructs. So any compliant compiler is expected not to produce an executable for them. So when a compiler does manage to produce an executable after compiling them, then they should show up as failure, which was the case here for this X test. So we do end up with some failures. So to investigate them further, we can run the streport command again with the same log file, and then attach a full option in order to see what exactly goes wrong with the tests. And as we can see here, we have one that complains about a missing operand and another that has 2 verification statements failing. So to take a deeper look, we can actually consult the tests individually. And to do that, we can open it up in our editor. And we can take a look at this test right here. And indeed, this X test has an erroneous form of the ternary operator and should not produce an executable. So the ternary operator syntax functions as follows. It should have a condition followed by a question mark, followed by an expression to be returned if the condition is true, followed by a colon, then an expression to be returned if the condition is false. And that is followed by a semicolon in the very end. So if, as you can see here in the middle, there is a missing operand, which is the one for the returned expression if the condition is true. And we have already been made aware of this failure, which is why for common failures like these, we typically have a comment outlining the failure and its analysis, so it can be consulted by the user. And here we already documented that the test incorrectly compiles on compilers that accept GCC extensions. So then we can take a look onto the other failing test, which was a t-test. So here we can consult this one. And in here, we can take a look at this test as well. So within this test, we have two structs, struct T and struct S, and we create an instance X of struct T right here. And we initialize its members with values. And then later on, we override some of these members by accessing the instance X with an initializer, which is this dot right here. And we override some of the members that were initially initialized right here. And we, in specific, override two members. Those are L and A at position 1. And those have their values changed from 43 to 41. And A at position 1 has its value changed from 19 to 17. And these verifications actually pass. So it correctly shows that L has been successfully overridden to 41 because this one passes. A at position 1 has also been successfully overridden to 17. However, if we recall the failures that occurred for the other two, namely K and A at position 0, however, during this partial override, K and A at position 0 were untouched. They were not changed. So we expect them to retain their initialized values, namely 42 and 18. However, we find that these two verifications actually failed. And the reason for this is that they incorrectly get reset to 0 during the partial override, even though they have been unchanged. And we have also been made aware of this as well. And therefore, we left a comment already. In general, the ideal approach for failing tests is for the erroneous constructs to be avoided in the user application. So that was it for this demo, and I will leave you with this final slide that will wrap up what I have shown you so far. So in this webinar, we have covered SuperTest's overview, details, features, and test suite, along with its feasibility in the compiler development and qualification procedures, as well as its configuration and reporting tools. So if you have any questions, you can please submit them now in the Q&A panel. I see we already have a few questions, so we can go through them. One question asks, how long does it take to run SuperTest? And that typically depends on how long it takes to run a test on your target. So running SuperTest for a host compiler would be very quick because the executables can be directly executed on the host as well. But for a cross compiler, you might need to flash and reset the embedded target for every test, as you have seen in the run test plugin, which took place in the demonstration. And that would typically be a challenge that would largely influence how long running SuperTest would take. Another question would be what is the benefit of SuperTest compared to a safety certified compiler that is commercially available? And for this one, the main answer would be in terms of flexibility. So with SuperTest, you can qualify as many compilers, compiler versions, and compiler use cases without any limitation. But pre-qualified compilers or safety certified compilers, these typically come with safety manuals that limit you in the ways you can use it. So, for example, it can say that the compiler is only qualified for a very specific set of options. In other words, the use case. And if you need to use a compiler option that is not part of those that are qualified, then qualification becomes invalid. On the other hand, as we've seen in this demo, there are countless amounts of combinations that can take place in the top-level configuration file. In other words, you have a multiple number of use cases for which you can use, and it can be configured to have any compiler option that you need, and it can then be qualified for that specific use case. Unfortunately, we are a bit running over time, so we will be happy to respond to any remaining questions individually by email. And thank you all again for attending. Please feel free to contact us if you would like to learn more via the emails provided at the bottom of this slide. And we'll see you all in the next webinar.